talk about time dilation, okay, we do understand that if you observe time from different frames of references, the time observed will be different. Okay, we have also seen one example where we said that a rocket is being launched into space, and when we actually measure that time from Earth, the time comes out to be 1.25 hours, right? So that is a good example of time dilation, but there we did not use a direct formula for time dilation. Today we are going to derive that. We're going to look into a concept which is called proper time and improper time. But before I start time dilation, let me just give you some clear picture of what are the ways to derive it. So we can derive time dilation relation from Lorentz equation or Lorentz transformation equation. We can do that. We will check that later. But if we actually want to do an experiment and derive the time dilation relation, it's a bit difficult because you cannot make a body move at such a high speed, right? So confirmation becomes a bit difficult with experiments. So there was a way out, and which is basically called a thought experiment. Okay, thought experiments are nothing but we are doing some kind of mental assumption, and we stick to the laws of physics, and we believe that yes, this will work. Okay, so we're going to do that thought experiment today and going to understand this. And in time dilation, the underlying concept is a moving person will say that my watch is slow. Okay, so if a person is moving, the clock will basically run slower. Okay, so it depends from which frame of reference you're observing, and you have to consider this also as relative. Okay, so there is a topic which we are going to learn later, simultaneous relativity. So what happens here is that even if I say an event is happening simultaneously together, right? An event A and an event B happens together, they may be considered to be simultaneous or happening together in one frame of reference. But if we observe that event from another frame of reference, they might not be together. Okay, they might not be simultaneous. So everything, whatever we have as a prospect in our mind, everything is relative. It just depends from which frame of reference are we observing. Okay, that's the underlying concept. So for our understanding time dilation, what we are going to do is, let's say we are going to consider a cylindrical chamber like this, and we have a mirror M1 connected on one end. Yeah. And we have one more mirror which is connected on the other end. Now imagine you are having a light bulb here. You're basically having a light bulb which is here, and it has the capacity of sending light signals. So it can send a light signal. Okay, that means a light pulse. You'll ask, why should we consider a light pulse? Because here we are considering speed or c. Okay, speed c. So for speed c, we will consider a light pulse. And in general, if it does not move and you are observing this within the system, you know that the light pulse will go here, hit mirror M2 and come back to M1. So that what usually happens. So there is an event 1, light pulse starts from M1, so it will start from M1, and event 2, light pulse will hit M1, and after reflection it will come back. Okay, that means it will hit M1 after reflection from M2, so it will hit M2, get reflected, come back. Okay, so that's the event that is happening, and such cases are something which we might have observed almost in our daily life. Okay, whenever we want to measure any kind of distance, time and so on. Okay, so we can easily measure what is the time here. Okay, so time between these events, right? So what are those events? You know it, events. So events. Okay, so if I want to measure the time, I have to know what is the total distance, right? So it has covered a distance of L when the light pulse starts, and then it comes back, so another L. So that means the total distance that it has covered is 2 times of L. I think this is clear, because I'm saying time between these events. What are the events? The first event was light pulse leaves this system. The second event was it comes back to the system. So how much time does it take? It is nothing but distance divided by velocity. So distance is 2L, and the velocity with which the light is traveling is c, right? Postulate of special theory of relativity, and let's just mark this as delta t. Okay, and this is actually something which you basically call it in S frame. So I hope we understand what is an S frame now, because I am inside this box. I'm sitting here and observing the event happening. Okay, so this is what is called the S frame. So now interesting is that suppose you are in another system and that particular system is moving. Okay, that particular system is moving. Okay, yeah. So what happens is, in general, we are going to observe this from a moving frame of reference. Now, if you want to observe this from a moving frame of reference, that means we are outside, okay, and maybe this frame is moving or our frame is moving, okay. So, the next part is, so as I told you, this is actually a thought experiment, okay. So, what we are going to do is this, okay. Let's observe the same. So when you write down in your exam, you have to write it in this way, okay, that is preferable, from a moving, okay, that means let's say S prime frame. So we have a moving frame and we are basically observing it from this. Okay, now I'm going to draw an image and I think it will be a bit clear to you. And let me just draw it on this side maybe. So we basically have this one. Okay. So what is this? This is the original frame and we know it's basically a moving frame of reference. So I will just mark this as M1 and M2. This is your M1 and this is your M2. Okay. Now, if you're observing it from a moving frame of reference, the light pulse leaves the signal at this particular point. But by the time it reaches M2, this entire frame is moving, as said. It moves to a new position. So let me just draw it with a new color maybe. Okay. So it moves to a new position. So when you basically explain it, probably you have to use some sentences and maybe we'll use it. Okay. So by the time the light pulse is, this is M2 now, and this frame is moving. Okay, this frame is moving. So initially when I was inside this frame, I know that the light pulse will go up and down and I'll be inside this frame. So I don't observe any kind of movement. Now I'm outside, okay, I'm somewhere here and this is moving in this particular direction. The light pulse leaves at a point, but by the time it moves, reaches M2, this entire frame has already moved here. It has already moved here, right? So maybe I'll just represent this light pulse by a straight line rather. Okay, I'll prefer using a straight line here. So it has reached at this particular point. Understand the scenario, right? Now what happens? The light hits the mirror and then it comes back to M1. But then by the time it comes back to M1, this entire frame again has moved certain distance. Okay, so maybe we can draw one more here. You don't need to use a color code. You can basically just draw dotted lines, I guess. That should also work. So this is again M2. Sorry, M1. Right? Bottom we have got M2. So what happens is light pulse goes here and then comes and hits back. So this is the scenario that is happening if the entire system is moving. Okay, and that is very important to understand right now. Okay, so what we do here is, okay, maybe I can just write down one line here which will make it a bit more clear. Okay, and this is like this. Okay, by the time I'm writing this down, but I hope you understand the point. If you can write it in your own words, it's fine. By the time the pulse reaches M2 from M1, so basically it reaches M2 from M1. Sorry, so it is M1 and it reaches M2. Okay, the tube or maybe the cylinder, whatever, the tube has moved because it's moving, so we know it has moved. So this is a thought experiment, and whatever logic we are using it here, we do realize that yes, this is true, it will happen. Okay, and it will basically again move maybe I can write down this: when reflected light travel from M2 to M1, travel from M2 to M1. Okay, so this is the idea, and based on this idea we can easily now find out what is the relation for time dilation. How? Let's just do it. Okay, so what I'm going to do is I'm going to use the Pythagoras theorem here. So I'll just take up this M1 and I mark this also as M1. Okay, and maybe we can just let me just write down this here. Therefore M1 M2 square, that means we are talking about this distance. Okay, M1 M2 square, okay, is this distance, which is nothing but L square, we already know. So maybe I can just write down an O here, right? So I think if I write down an O, I think it will be more clear. So I can simply write it down as O M2 square plus O M1 square, right? So this is your O M1 square maybe, and this is your O M2 square. So you're just using Pythagoras theorem and finding out the result. Even if you don't do it, still you can find out the answer. It's very easy, right? It is basically O M2 square. So O M2 square is nothing but the length, which is nothing but L square. So we already mentioned that the length is L. So I can take this as L square, okay, plus O M1 square. So O M1 square is nothing but the distance, that tube covers in time t, okay, when it is moving with, let's say, a velocity v. Okay, so this tube is not moving with the speed of light, mind you. This tube is not moving with the speed of light. The light pulse is moving with the speed of light, so that's c. But this tube, maybe it's moving with a velocity v. So in this direction it's moving with a velocity v, and if you want to find out the distance, this would be nothing but velocity into time. So I can just simply say v into t. So that's the distance, right? So this is the first time that we are basically considering. So maybe I can just write down this as t1. So it's simply v t1, okay, square. Okay, so this is the relation that turns out to be this. So we can say that m1 m2 is equal to root over L square plus VT1 square. Okay, so let's take this, and now what we are going to do is we are going to use the postulate that we already know. Okay, that m1 m2, that means this distance, since it's the light pulse, we know it is distance is equal to time into speed, right? And we know in any frame of reference the speed of light won't change by postulate. This distance that we are talking about, m1 m2, is equal to nothing time, and we are talking about the speed of light here, because the light pulse is traveling from this point to this point, and speed does not change whether it's any frame of reference, if it is inertial c, and the time is obviously that same t1, right? So if that is the case, we can just simply write it down as ct1 is equal to root over L square plus VT1 square, right? So now we can just simplify and find out the answer for your time dilation. Okay, we just keep doing, and we have to do some more steps here. Okay, so in general, if I just write it down, I can just simply write it down as, let me take it on this side, L square plus VT1 square is equal to C square T1 square. Interested in time, so I'll just take t1 square on one side, and then if I take t1 square here, I can take common with the v's, right? So this is v, right? V square, I guess. So this is v square, so t1 square I can take common, okay, and then I can simplify this. This would be L square divided by it will be c square minus v square. So you have to just simplify this, and I think you can do it. C square minus v square, right? So you can take it on this side, you get c square minus v square, and then you have got t1 square, okay, and L square divided by c square minus v square. So this will actually give me what is the relation for t1, and t1 is equal to L square root of that divided by root over of c square minus v square, right? But then we are supposed time. This is the first time. That means the time that it takes or the light pulse takes in traveling from M1 to M2. The next time that we have to calculate is the light traveling from M2 back to M1, and that will actually give you T2, right? So let's just calculate what is our T2, okay? So I hope you have the image clear. So we really don't need to check the image now, I think. Okay? So we can say similarly for M2 to M1, right? The time is same, right? It is the same as per geometry. You can check it, okay? We know that it's basically traveling with the same speed v. So I'm not going to do the calculation. So it's the same thing, right? So if we just observe this once again, it's the same thing. You can do the calculations, but you're going to land up with the same result. So T2 is also going to be the same, okay? So if T2 is same, T1 is same, we can actually find out the total time, right? So therefore we can say total time. These sentences are important, okay? I prefer you write it down because it's basically going to be a descriptive question. If you're just going to write down the mathematical part of it, is going to be a bit short, okay? So that's important. Travel of light, total time, okay? Light pulse. Even if you don't write down, this is fine. This is just a note for you from M1 to M1. Okay, M1 to M1 I'm writing. Okay, it's M1 and back to M1. Okay, after reflection from M2. So I hope you understand what do I mean by total time after reflection from M2, right? So therefore the total time is nothing but 2t1, because even if you take it to t2, it's fine, it's the same result. So you can just add them up. This is 2t1, 2t1, that means it is 2 times of L divided by root over of c square minus v square. And we in general write it down in terms of this relation. If you remember, I told you about beta and gamma divided by root over, if you take c square out, it will be just c out of the root, 1 minus v square divided by c square, right? This is the time that you observe when you are having it in the moving frame of reference. So I'm just writing it down as delta t prime, right? So let's just get back to that relation. This is the relation delta t prime which we are getting when we are considering the moving frame of reference. And when we are saying that it's in the same frame of reference, this is the time, delta t. And you see, both of them are connected. Delta t was 2L by C, and here the relation is 2L by C root over of 1 minus V square by C square. That means 2L by C, we can just replace it, right? So that's simple and it's done now. Okay, so in S frame, delta T is equal to 2L divided by C. We have already observed it, right? So can we have under 1 minus V square upon C square is gamma? Yeah, you can directly write it as gamma, right? Yes, yes, you can do it, right? But then very important, whenever you write down this as gamma, just should mention in the bracket that gamma is equal to 1 divided by root over 1 minus by V square by C square. But let me tell you, most of the book does use the notation gamma, so this is very common, okay? So we can write it down, okay? It's just for, making it look better, more neat. Therefore, in S dash frame, we can have delta T is equal to 2L divided by C, right? So we basically can have it, okay, in S frame. Maybe I can just try to like to write it down very clearly so that you are not confused, okay? In S frame, so sorry, this is S prime frame. So already written it once, I don't need to write it down. Therefore, in S prime frame, we can write it down as delta T prime is equal to 2L by C is nothing but delta T. So I can write it down as delta T divided by root over 1 minus V square by C square. Okay, so this is the relation that we are actually looking for, and this entire concept comes from the special theory of relativity. So you see, this is the time dilation relation. That numerical problem that we have done, even if we do it using this formula, we can actually find out the relation. Okay, so this is time dilation relation. Very important. Okay, so if I tell you how much marks will it carry, so you can also in general you can also write it down as delta t prime is equal to gamma into delta t, but then just make sure you know what is gamma, or you can write it down as delta t divided by root over of 1 minus beta square. So beta is equal to v by c. Okay, so any kind of notations are basically used, just make sure that you mention notations full form, that is important. Okay, so this is the derivation. I don't need to write down these things, just derive it, that's it. Okay, and this doesn't carry too many marks, it will be basically 3-4 marks maybe. Okay, so this is again important. So this is time dilation, and if we look into our problem that we have derived or done in the last class, okay, if you recall this particular problem can also be solved using this time dilation relation, but I'll leave it to you. Okay, you can try it, but I'm going to do some problem maybe today if you get time, so that you understand a bit of it using some numerical problems. Okay, but then as I told you, this is not the only way to derive the time dilation relation. This is a thought experiment we basically use. We can also use time dilation relation from Lorentz transformation. Okay, so the next topic is time dilation, and if we keep on doing this, we get a clear picture of what exactly is the frame of reference, where do we use it, when do we use it, time dilation, and so on. So that's why this is time dilation from Lorentz transformation. So Lorentz transformation, we already have the relation, we are just going to use it to find out the relation for time dilation. Okay, so we are going to assume some things here. Okay, and I hope it will be a bit clear. Let me just write it down. What we are going to do here is we are going to consider two events. We are going to consider two events. Let's mark them as E1 and E2, and they are in same frame. And same place. So what does it mean? It's the same frame of reference, it is at the same place but at different time. Okay, so maybe there is a bulb which glows, and then that bulb is removed, another bulb is put in, and then it glows. Okay, so both the bulb will glow at the same place, okay, at the same frame of reference but in different times. Okay, so that is the interpretation we are doing it right now. So that means for event 1 it will be x y z coordinate but in time t1, and event 2 will be the same x, y and z coordinate, but this time it will be time t2. So if you want to derive this from Lorentz transformation, this assumption is very important. Okay, so this was in S frame. What happens in S prime frame? Okay, in S prime frame, okay, this event 1 will be, now this is interesting. Okay, in S prime frame it will be different because S prime is moving. Okay, so I hope you understand by the previous logic. Okay, let me just write down the first event. It will be x1 prime, y1 prime, z1 prime and t1 prime. So if an event is happening here and this is your S frame and this is your moving frame, okay, maybe this is moving in this direction. So when I see the first event happening at time t1, this was here, but when the second event happens, relative to this has already moved a different position because it was the moving frame here. So that means I am observing the second event at a different position. So this should be very clear to understand and derive this time dilation relation from Lorentz transformation. X2 frame, Y2 prime and Z2 prime in the time T2 prime. Okay, so E1 and E2 will appear in a different position. Okay, appears in, and this is quite logical. Okay, different position. So imagine this, you are inside the bus, okay? One event is you are here, your friend is here. One event is your friend is switching on the bulb. The bus is moving with a velocity v. So one event is your friend is switching on the light and then switching it off. That is one event gone. You are observing at this particular point and your friend is not moving inside the bus. The second event is again your friend switches on the bulb and switches it off. So both the times if you are observing it from here, you are observing it here itself. There is no motion, there is no change. Okay. Now maybe this is switched on. The first event is it was the bulb was switched on in MIT University, and the second unit the bulb was switched on in Jaipur city. Okay, so that means that at two different positions, but for you it's the same position because you are inside the moving frame. Now suppose you are standing in front of the gate and your friend has switched on the bulb and you are observing the bulb here. The position is at the near the gate, right? But then again your friend switches it off and somehow you are able to see it maybe online, and the bus has already moved to Jaipur. So you are observing it at two different positions. This is one position, this is one more position. So that's the basic idea what we are using it here. Okay, so it's a very simple concept. So there we can use the relation that we have from Lorentz transformation. What was our relation? Our relation was T prime is equal to T minus Vx divided by C square divided by root over of 1 minus d square by c square. You can write down gamma. But there are two times here. One is t1 prime and t2 prime. So let me just find out what is t1 prime. So t1 prime is equal to t1 minus vx by c square. This will remain as x because whether you take this event, first event, or you consider the second event, both the cases this is x. This is also x. So there is no logic using x1 here. This will remain as x. Okay. So that's the underlying idea. And if I take it for the second event, the second time t2 prime, the time will be different. So this will be t2 minus v constant velocity because inertial frame. That's why Lorentz transformation. This is x. This will remain as x. Okay, because in the stationary frame x does not change. In the moving frame x changes. Divided by c square divided by root over of 1 minus v square by c square, right? So what you want to do, you want to find out what is the time difference. That's the idea, right? Time dilation means you're going to find out what is the time difference, right? So let's just find out what is the time difference here. So therefore we can say t2 prime minus t1 prime. We can just subtract one from the other, and maybe I'll just write it down as gamma. This is t2 minus vx divided by c square, okay, and then minus gamma t1 minus vx divided by c square, right? So we can open the bracket. This we can see this is nothing but gamma into t2 minus t1, okay, and this is minus vx by c square, this is minus plus vx by c square, so these two terms will cancel out, right? So this is your gamma t2 minus t1, and when we talk about t2 prime minus t1 prime, we are talking about a time interval, and that's the logic behind delta t, right? It's a very small time interval that we are basically considering. So this is delta 2 t prime, or we can just write it down in the prime frame of reference. We can just simply write it down as this, okay, delta t prime is equal to gamma into delta t. So it's the same relation that we are getting. But what we understand from here that we can use Lorentz transformation, but we have to realize the scenario. So even if I don't draw a figure, this thing should be very obvious to me. Okay, so the example that I've given, the bus example, you can take that logic. Okay, so for example purpose, whenever I'm asking a question about 4 or 5 marks, the question actually deserves some respect, and that's why 4 or 5 marks the answer should be a bit long. So you should always take this thought experiment formula. But if I specifically use Lorentz transformation to show that this is the relation, time dilation, you can do this. But then in case I don't mention anything and you do it by Lorentz transformation, still I'll give you marks. I cannot deduct, right? Because that's obvious. So if I clearly mention Lorentz transformation, go for this. Okay. If I just say time dilation, relation, derivation, probably you should go for the previous thing. Okay. Because that's just for marks. That's it. Okay. bad system we have, but then anyway, if you do it, still you are going to get some marks. Okay, so this relation, okay, both sides, whatever we see, there is some terms that we should know which is used but not often. On this side, we basically write it down as the time that is being measured from the prime system, and this is actually called improper time. Just a term, improper time interval, okay, is equal to gamma, and I think you can guess this is proper time interval. Okay, this is called proper time interval. So if you are in the same frame of reference and you are measuring the time, you are doing a proper time interval. So that space rocket example that we have taken, where we found out that this delta t prime was 1.25 hours, but then delta t was equal to 1 hour. That means if we have the watch on the spaceship, the time that we measure is proper time. If we have the watch on the earth, on planet earth, we're basically measuring the improper time. Okay, a very simple example might be, imagine you are traveling from station A to station B, and there are two watches, one in station A and one in station B, and you are also having a wristwatch, and you are in the train. The time that you measure will be actually a proper time. The time those watch measures, by the time it reaches station B, those will be nothing but the improper time. So based on this, I am going to take an example or a numerical problem, and you are going to see something very interesting here. Okay, so यहाँ पे क्या होगा? We are going to see that the improper time that we are talking about in our daily life is very much insignificant. Okay, so let me just give you this problem, and you solve it and tell me what is the time that you are getting. And don't ignore, because if you feel that okay, 10 to the power minus 14, 10 to the power minus 10 लेके भी क्या करें, छोड़ देते हैं उसको. We usually ignore it, right? But then for understanding this concept, we basically cannot ignore this. So I will take this numerical problem, and these are tricky. Okay, if I'm asking you a question in exam also, if you just think about it, you will feel that okay, the answer is very simple, you can derive it very easily. Okay, this question might look a bit complicated, but then it's not. Let's derive this and understand. So a person is traveling, okay, at a speed of 180 kilometer per hour. That's the speed, right? So that's in a train, so I'll just take it as in a train. Okay, his watch reads, so understand this question, this is very interesting. Okay, reads 5 hours, okay, in traveling from station A to station B, station A to station B. So he has a watch in his hand, and it takes this much time to travel from station A to station B. There are two parts to the question. Okay, and the first part to the question is, as per station watch, how much time did the train take to travel? Did the train take to travel? Okay, you ask a layman this question, वो बोलेगा क्या question है ये, बेकार question है, right? But since we are into science, and we are actually taking up this topic of relativity, we do understand that the time that the station watch will read will be different from the watch that my wristwatch is going to read. Okay, so this is important. And one more question is, we can also find out the uh, distance, okay, from Earth's frame what is the distance between the stations. Between the stations. So why this question is interesting, because this is going to tell me that in your real life we really don't realize time dilation happening, because this is very insignificant because of the speed. Okay, so you have to do this calculation. You already know what is the proper time, and basically you are going to use this relation. Okay, so instead of mentioning every time about delta t prime and delta t, probably if we take it in this way, I think this looks much more simpler concept. Proper time divided by root over 1 minus v square by c square. So if I want to find out what is the improper time, okay, I have to use this. So proper time, it's already given to be nothing but 5 hours. Improper time you can calculate after you replace this v with 180 kilometer per hour. Of course, you should convert it into meter per second, because c is considered to be in meter per second, and do the calculation and check what is the order of the time. Okay, so that's important. But then I just like to tell you here that, you know, from this particular formula, this is also obvious, okay, that the improper time will be longer compared to the proper time. Okay, because this is divided by a value which is less than 1, right? You take a value and divide it by a value which is, let's say, greater than 1. So you are going to get a result which will be greater than the whatever is on the numerator. But if you are taking up a value and dividing it with a result which is less than 1, okay, then the entire result will always be greater than a, right? So that is the idea here. Okay, so that is why improper time, when we talk about, we actually get a dilation. Dilation means elongated, so time dilation. Okay, so you can do this calculation and see what's the answer that you are getting. Okay.